Okay, so same thing. This is our L of S. I'll go through this a bit quicker, not super quick because I'm still not that good at this. So our first 0, our first and second poles, and our third pole is -12. And so same thing as before, we're going to have 3 branches because we have 3 poles, and we're going to have 2 branches going to infinity because there's only 1 0, but there are 3 poles, and you need somewhere to end. If you can't end, you gotta go end at infinity. And then we will calculate let's draw it first. Okay. So we have 1 and 2 at 0. Make this slightly smaller, I guess. Pull at -1, and then way off to the side, we've got a pole at 12. That's probably not to scale, but close enough. And same thing as before, this line is definitely going to be included in our root locus, and it will exit from here and enter here, but there might be some weird behavior in between because it's so long that we're just going to go and ignore that for now. So now we need to calculate where our asymptotes are going to go. So alpha is the sum of your poles minus the sum of your zeros divided by n minus m, which is going to be equal, in this case, your poles are -12 plus 0 plus 0 minus a -1, so it's a +1 because our zeros and our poles are negative, and we'll divide that by 2. So that's going to give us -11/2, so 5.5, -5.5. And that will happen around slightly less than halfway, around there. And I'm not going to repeat the calculations for the angle. We're just going to steal it from here. It's exactly the same because there's the exact same, n and m are exactly the same. So I'll just paste that here. And we can just immediately draw our asymptotes. That looks more like 45. So the lines of your asymptote should be equally spaced, so these angles should all be equal. 360 divided by 3, they should all be 120 separation. That's basically what this equation does. Okay, so now we have our asymptote. Why did I draw it? Okay. Ignore those lines. I stole it and I still drew them wrong. Okay, this is the up and down one. Yeah, what? N minus m is 3, that's what it looks like, but n minus m is 2, so it's these 2 angles. I probably should have just recalculated it. But, so that's what it should look like, same as before. It's kind of what we started with. So it's like, okay, you would think it looks the same, right? But it does not for some unfathomable reason. So, if we take our characteristic polynomial and we rewrite it so that k is on one side, we'll get, I don't trust myself to do math. You get that, and then you take the derivative of k with respect to s, and you will get, okay, some more product rules. Plus s to the third minus 12s squared, negative 1 s plus 1 to the negative 2. Rewrite that. And set that equal to 0. And do a bit more rearranging. If you're good at mental math and you can do this in your head, congrats, but I can't, so here we are. Okay, and we combine our like terms again. So basically the overall process is the same, but we're going to have a result that's slightly different. Do a bit more factoring and getting rid of the negative. We'll get s is equal to 0 and s is equal to negative 15 plus or minus radical 15 squared minus 4 times 2 times 24 over 4. So if we check this term under the square root, I'm going to get 15 squared plus minus 4 times 2 times 24, you'll get 33. So we're going to end up with a real number here. And that real number will be plus, it will be negative 2.31, and also for minus, it will be negative 5.19. So at these 3 points, you're either going to have a break-in or a breakout from the real axis. So if we go back to our graph, this is 5.5. So we're going to have break-in and breakout points at 0, at 2.3, and at 5.19. Negatives. So from there you can kind of go like, okay, so we have poles here, so you want to break out here, and you can kind of guess that's going to go like blop, blop. So the branches come out of the poles, they come and collide with each other at negative 2.3. And then they're going to split off to the left and the right sides. One's going to go to the pole at negative 1, and one's going to go towards the, it's going to go towards infinity. But from the other side, from our pole at negative 12, we also have another branch coming in. And so those two branches are now heading straight for each other, and they're going to crash into each other at the green dot. And that is where our third breakaway is going to occur. And breakaway points, when you have two branches coming together, are going to always break away or break in at 90 degrees. So either 90 or negative 90. And then these branches will go off and start following our asymptotes. And that's our root locus. So if you compare this to our very, very similar looking, if if you look at these two equations, they look very, very similar. The only change we made was 4 to a 12. But it resulted in a root locus that looks really, really different. So you have to calculate your break in and breakout points in order to know if something weird like this is going on, or else, like me, you would try to graph it like this probably, because that's what I thought it would look like. So calculate your break in and breakout points. And I think I have another example here. Did this before where yes. So if we didn't have that extra third pole, that's this example, you would end up with something that looks very similar to the one where we had a pole at negative 12, because negative 12 is pretty far away, so it's kind of like it's going towards infinity, and so it's going to have very similar behavior to if it's kind of like if your L of s was s plus 1 over s squared, and then s plus infinity. So negative infinity is your root. That's what the 12 is doing.